Hello everyone, and welcome to your video tutorial over gravitation. In this tutorial we will be talking about the Universal Law of Gravitation and the equation for that, and the types of problems that you can encounter with that equation, and just the types of problems that you'll see in general. Okay, so Newton postulated that every single object in the universe that has a mass exerts a gravitational force on every other object. So let's say I've got two masses, and let's label them a little bit more clearly, M1 and M2, and the distance from their centers, I will call that a distance r. Again, it's important to note that's the distance between the centers. Okay. So he came up with this gravitational equation that starts out with this capital G. Now, capital G is the universal gravitation constant. And there have been several experiments done to calculate this, and it is known to be 6.673 times 10 to the negative 11. Now, we'll talk about the units here in just a second. Okay, so then it's capital G times M1 times M2 all over R squared. Okay, so the units on G. Force seems to be in newtons. So that means I should end up with newtons on the right side. Well, mass times mass gives me kilograms squared over R squared, which would give me meters squared. So that means that I don't have newtons yet, so gravitation has to have newtons. But it has to cancel everything else. So it would have meters squared on top times kilograms squared on bottom. So it's Newton meters squared over kilograms squared. So this equation right here, it's one that's given to you on your formula sheet, but again, it's not given to you for the multiple choice. Okay, so how is this different than before when we were talking about, okay, well, my weight is just mass times gravity, or Fig Mig, where we said gravity was 9.8 meters per second squared. Well, we get that from this equation. 9.8 is a pretty good approximation of how things accelerate that are close to the surface of the Earth. Okay, so let's say that I have the Earth here, and I am standing on the surface of the Earth. And again, it's probably important to note that this is not to scale, because if it was, I would be a giant. Okay, and so let's say that I have a mass, I'm a person, so mass of a person is 70 kilos. And then let's say the mass of the Earth is 5.972 times 10 to the 24th kilos. So just a smidge bigger. Okay. And the radius of the Earth from the center out to the surface is it's 6,378 kilometers, but we need everything to be in meters, so that would be 6.378 times 10 to the 6th meters. Now, when I'm standing on the surface of the Earth, I might add, from my center of gravity, I might add maybe 1 meter, less than that really. Let's just say I add 1 meter to that. Well, percentage-wise, you can see that changing the overall radius of the Earth, if I add 1 meter to this number, it doesn't really make that big a difference. You wouldn't even see it in our estimation here of the radius. So we're just going to say that if I'm standing on the surface of the Earth, then R is just radius of the Earth. Because not only does adding 1 meter not really affect the radius, but think about the equation, I square R. So that 1, if I add 1, it really doesn't just affect it a whole lot. Okay, so let's calculate the force due to gravity when I am standing on the surface of the Earth. So I would have G, mass of the Earth, times the mass of the person all over the radius of the Earth squared. So let's plug in our values. I've got 6.673 times 10 to the minus 11th times the mass of the Earth, which is 5.972 times 10 to the 24th, times the mass of my person, which is 70, all over the radius of the Earth squared, which is 6.378 times 10 to the 6th. Oops, not taken to the 6th, but squared. Let's just cross that out and say squared. Okay, so let's get out our calculator here, and let's do some calculating. 6.673 times 10 to the negative 11th times 5.972 times 10 to the 24th times 70. That gives me, on Zitto, let's just go 2.79 times 10 to the 16th, all over 6.378 taken to the 6th power squared gives us 4.068 times 10 to the 13th. Okay, so now let's divide that through. 2.79 second e to the 13th divided by 4.068 and the 13th. Okay, so I get 685.8 newtons. Now, using our Figmig, which is mass times gravity, I would take 70 times 9.8, and that gives me, look at that, 686 newtons. So, pretty close overall. Now, how do we get this g, lowercase g, for 9.8 meters per second squared? Well, if you think about our equation right here, mass of the Earth, mass of the person, right here, that's the mass of the person. So that means that g, mass of the Earth, over r, radius of the Earth squared, that's how we get our acceleration. Now, you might ask, well, how do we get that? Well, the units on g were Newton meters squared over kilograms squared, so times the mass of the Earth, which is in kilos, over r squared, which is meters squared. Okay, so my meters squared cancel, and one of my kilos cancels. Well, that leaves me with units or newtons, but g has to be in meters per second squared. Well, you might remember that a newton breaks down into a kilogram meter per second squared. So that's my n, and then I'm multiplying by 1 over kilogram. And oh my gosh, look at that. That is how you can figure out g on any planet that you are on. If you know the mass of that planet and the radius of that planet, you can figure out the acceleration of that planet, or its g value. Okay. So let's talk about some applications of this gravitation equation. Let's say that I have an object orbiting another object. So I'll call this M1, here's M2, oops, M2, and they are a distance r. Okay, well, let's say that it is orbiting in a perfect circle, so that r doesn't change. We'll talk about how orbits are all elliptical, but for our intents and purposes, a lot of times the orbits can be considered circular. Okay. Now, let's talk about what force is acting on M2 and what force is acting on M1. They both have a gravitational force that is always directed along r. And if I've taught you anything about circular motion, any force that is directed along r is your centripetal force. Ooh, well, what we know about a centripetal force is that I can set it equal to my mass times my centripetal acceleration. Okay, well, let's talk about what mass is actually accelerating. If we consider objects that, for instance, planets, let's say this is our sun. and this is maybe the Earth. The sun itself, compared mass-wise, it might as well be us standing on the Earth. I mean, it's just huge in comparison. Now, they both exert an equal and opposite force to each other, but think about force equals mass times acceleration. Well, the force on the planet, or on both, is still Fg. The thing about the mass of the sun, it's huge, and so its acceleration has to be very small. So we're going to say that the only object that is accelerating is m2. So the centripetal force is the force due to gravity. Well, that equals m2 times its centripetal acceleration. Now, we know that centripetal acceleration is v squared over r. And I know that the force due to gravity is capital G m1, m2, all over r squared. So I can set these two things equal to each other. And I can solve for all kinds of stuff. I can solve for the orbital speed of the planet. Once I have that orbital speed, I could solve for the period of the planet, which the period would be equal to a year on the planet. And so there's all kinds of things that I can solve for this. There'll be another video tutorial later that will look at the types of problems that you'll encounter with this equation.